So in this first part of trigonometry, what we're doing is going to use the trig identities to help us solve trig equations. So what we're going to do in this video is go through the following 6 examples, which all look at using the trig identities to solve equations within a given range. So let's get started on this first problem then. So what I've done here is worth noting what the trig identities are in its entirety. So in each of these questions, I'm just going to have this in the corner of the screen, so as I'm referring to it, you can see where all of these are coming from. So for the first one, we're asked to solve the equation of sine theta equals 2 cos theta for the range of minus 180 to 180. So the first thing I want to do is try and think. Now, one question I always get asked when I'm teaching my students trig identities is them asking, well, how do I know which rule to use? Now, as you can see with regards to the rules, the identities we've got in this red little cloud, is that there's only one. This identity here is the only one that uses a single sine x and a single cos x. So when you have got a mixture of sines and coses, your general theme is to use this identity, the top identity, to try and somehow combine the two to get tan x. So because obviously the remaining 3 identities all use a degree of 2, so they've all got sine squared or cos squared. So going back to this original question, what we've got is we've got sine theta equals 2 cos theta, and my aim is to try and get sine over cos, so it combines to become tan theta. So if I take the cos theta or divide both sides by cos theta, I get sine theta over cos theta, and that equals 2. This then combines to become tan theta equals 2. So theta then becomes the inverse tan of 2. And then if I type that into my calculator, I get my first angle of 63.4 degrees. And if I then use the tan graph or use cast, I can then find the respective other angles within the given range of minus 180 to 80, in which my other angle is going to be 116.6 degrees. And there is my final answer. So moving on to our second example. And then behold, we've got this. So as you can see here, we have got a squared in there. We've got cos squared theta, 2 cos squared theta minus sine theta minus 1 equals 0 for the range of 0 to 360. So again, I refer back to my list of trig identities, and as you can see, what the main objective when you're doing these types of questions is, when you've got mixture of trig identities, is to try and get them so that you just have one. Because when you have one trig ratio, it's then easy for you to then go on and solve, like we've done in the previous trig equation videos, of quadratics or simply using the graph, and we can go forward from there. So as you can see, now if I was to do something with the sine theta, now there's only one trig ratio which uses, I can see a single sine x, which is the top one. Now the problem about me using the top line is that if I then make sine x the subject, I'm going to end up with something with tan x and cos x. So I'm actually introducing more trig ratios into this equation, which is something that I don't want to do. So I've got to do something with the 2 cos squared theta. Now looking at this, I've already got a single sine theta, and this is something you want to look towards. So what I'm going to do is I'm actually going to use this bottom trig ratio here, and I'm going to swap cos squared theta for 1 minus sine squared theta. So what I've got is I've got 2, and then I have 1 minus sine squared theta minus sine theta minus 1 equals 0. Now as you can see from that line, although I've got a sine squared theta, I've just got one single trig ratio. So now I've just got something involving sines. Now if I expand the brackets out, I get 2 minus 2 sine squared theta minus sine theta minus 1 equals 0. Now if I take all of this to the right hand side, and the reason why I'm doing that is because I've got a negative 2 sine theta, and this is slowly starting to look like a quadratic. So I want to deal with a positive x squared, or in this case a positive sine squared theta. So if I take everything all onto the other side, then what I end up with is 2 sine squared theta plus sine theta minus 1 equals 0. And now it becomes like a quadratic equation. So the first thought is, does this factorize? Which in this case it does. So I've got 2 sine theta minus 1 and sine theta plus 1 equals 0. So my two solutions I'm going to get are going to be 2 sine theta minus 1 equals 0. So sine theta equals a half. With this, I'm going to end up with sine theta plus 1 equals 0. So sine theta equals minus 1. Now, I haven't finished this just yet, but what I'm going to do is get a thinner pen because I can see that I'm running out of screen. So from this, now if I just label this hashtag 1 and this one hashtag 2. So from hashtag 1, what I've got is I'm now going to solve sine theta equals a half. So if I just write this out just so you can see what I've done, I get theta equals 30 degrees, and then using my graph I get another value of 150 degrees. Now using the second equation, hashtag 2, I've got sine theta equals minus 1. So if I do the inverse sine of that on my calculator, I get a value of minus 90. And using my graph, I then get another angle of 270. Now, as you can see, if I go back to the original question, it's only asking for values within the range of 0 and 360. So with this, I have to discard one of my angles, which is the minus 90. However, I needed that minus 90 in order for me to find the 270. So my final answer in this question is going to be 30, 150 and 270 degrees, and there is my final answer. So moving on to our third example, in this question we've been asked to solve tan theta equals 4 cos theta for the range of minus 180 to positive 180. Now as you can see in the initial equation that we've got, I've got no powers, so the only trig identity I can initially use is going to be tan x equals sine x over cos x. So if I go about replacing tan theta with sine theta over cos theta, and that equals 4 cos theta. Now from this, there's not really much I can do, because if I was to swap sine or cos for any using the trig identities, I'm only going to end up going back to the initial question. So one thing I can kind of think about doing is taking the cos theta over to the right hand side. Now if I do that, I get sine theta equals 4 cos squared theta, and now I have got a power. So here I've got cos squared theta. So now what we're now going to do is replace cos squared theta for 1 minus sine squared theta, and one of the reasons why I want to do that is because by doing so, what I'm going to end up with is now I've got an equation that just involves the trig ratio of sine theta. And now lo and behold, what is slowly starting to look like if I expand the brackets out is it slowly starts to resemble a quadratic equation. So if I take the right hand side over to the left hand side, and again, main reason for this is to try and get my sine squared theta positive. So I get 4 sine squared theta plus sine theta minus 4 equals 0. I now need to go on and solve this. Now, just being a bit more going into blue beta mode, I've already researched this and this does not factorize, so it doesn't factorize. So what I need to do instead is use the formula. Now if you've got a calculator, you can just go straight into solving this, which is something that I probably would recommend that you do. So I get a sine theta value of 0.39 or minus 0.64, and those answers are to 2 decimal places. So if I just call this hashtag 1 and this hashtag 2 because I need to find the respective values of theta for those two values, and I'm just going to take it over here. So here I've got sine theta equals 0.39. If I do the inverse sine of 0.39, I get a value of 23 degrees to the nearest degree, and then if I use the graph or use cast, whichever you prefer, I get my second angle as 157. And lo and behold, they all lie within the sort of ratio. Now if I just quickly do my graph, so here all I'm interested in is this region here, and so what I can then do is, oh, don't do that, so let's get the x-axis back, is I get something that looks like this. So all I've done is, this is where it's 0.39 and this is where it's 0.64 minus. So what I now need to do, so the calculator gave me this first initial value, I've used the graph to find my second value. Now if I do the inverse sine of minus 0.64 on my calculator, I get a theta value of minus 39.8 degrees, which is this value here. And then using my graph, I can then work out what that second angle is going to be for this particular part of the equation, which is minus 140.2 degrees. So my final answer, and again, like I said, it's always good practice for you to write out all your angles in a nice neat row. Don't be too concerned about the order, because I can see here that my numerical order has gone a little bit bodgy. And there is your answers for that particular question. So if we move on to question 4 by scrolling down, and let's just move this up. So from here, as you can see, we've now got cos solved, where we're asked to solve 1 minus sine squared theta equals 3 sine theta cos theta for the range of 0 to 360. Now this looks like a bit of a mess, and sometimes when dealing with trig identities, sometimes you can go in a bit of a rabbit hole and you might get stuck. But it's all about trial and error, and with practice you will get there. So looking at this and trying to resemble what we've got something that resembles a power. Now one thing I can definitely see straight away is that I recognise this 1 minus sine squared theta, because 1 minus sine squared theta is equal to cos squared theta. So what I'm going to do here is replace this with cos squared theta equals 3 sine theta cos theta. Now from this, what I'm trying to do is, again, my main objective is to try and get a single trig ratio, is if I now divide both sides by cos theta, then what I end up with, so cos squared theta divided by cos theta just ends up with a single cos theta, and 3 sine theta cos theta divided by cos theta, so those cos thetas cancel out, and lo and behold, I end up with just 3 sine theta. Now again, might not seem like we're doing much because I've still got 2 trig ratios, but what I should be able to now spot is I've now got a single cos theta and a single sine theta. So what I now want to do is use that top identity of tan x equals sine x over cos x. So from that, I'm going to take the cos theta over to the other side and take the 3 over to the left hand side, and what that will then slowly look like is it'll look like a third, and I've got sine theta over cos theta. And swapping those around and simplifying it, that means I get tan theta equals a third. So going about solving this, if I then do the inverse tan of a third, I get my first angle as being 18.4 to 1 decimal place, and then I get a second angle of 198.4 degrees, and there are my 2 answers. And again, just to double check, it's worth always doing a bit of a sketch of what it is you're actually looking for within the given range. So there is my tan graph between the values of 0 and 360, and if I draw a line of a third, you can see that I'm only expecting 2 possible answers, and just to, it's kind of like validates my 2 angles that I've got here, which is being. So in my 5th example here, we can see that we've got no powers, so the only sort of trig ratio I can potentially use is going to be this top one. So going from there, the only thing I can kind of replace in this particular question, so where we're asked to solve tan x sine x plus cos x equals 2 for the range of 0 to 360. So the only thing I can change is this tan x. If I go about doing just that, I get sine x over cos x. What I'm going to do is I'm just going to put that in brackets so you can see what I've replaced, and then I've got sine x plus cos x equals 2. So from this, if I then simplify this little bit here, I get sine squared x over cos x plus cos x equals 2. Now, some of you might be thinking of, well, now that I've got sine squared x, let's swap it for 1 minus cos x, but you can do that, and you might go a way of doing it, but my initial thought is to try and write this as a single fraction. So what I'm now going to do is I'm now going to write cos x in the form of a fraction where my denominator is going to be cos x. So what I'm going to do is if I write sine squared x over cos x plus, now if I turn this into a fraction so I've got a common denominator, in where the common denominator is going to be cos x, I get that. And all I'm going to do is put that in brackets so you can see what I've changed. And then I can write this as a single bracket as sine squared x plus cos squared x all over cos x equals 2. And what I notice from this is, using the trig identity of sine squared x plus cos squared x equals 1, and I've now got that here, I can rewrite this as 1 over cos x equals 2. Now if I rejig all of that around, so I take the cos x to the right hand side and the 2 over to the left hand side, then what I end up with is cos x equals a half. So then if I then go about working what that is, so I've got cos x equals a half. So on my calculator, if I do the inverse cos of a half, I get a value of 60 degrees. And if you remember what the cos graph looks like between 0 and 360, so that starts at 1, and here is my line of a half, and so that there is 60, so this value here is going to be 300, and I get my second angle of 300. And then finally, moving down to our last example. So here, so we've been asked to solve sine squared x plus sine x cos x equals 0 for the range of 0 to 360. Now, one thing to look out for is don't automatically go stretching for the fact of using these trig identities that we know. Now, as you can see from this particular equation here, I've got 2 terms on the left hand side, and I'm thinking, right, what have both these two terms got in common? Well, both of them have got a sine x. So one thing that's quite sneaky, and sometimes you won't see it unless you've been told it, and which I'm hoping that by telling you this, it'll be now something that you spot. As I've got a sine x in both these 2 terms, what I'm now going to do is take out a sine x from these 2. So what I'm going to end up with is, if I factorize this, I end up with that. Now, one thing I could have done is I could have changed this for cos squared, 1 minus cos squared x, but again, there's nothing much I can do with this here because I'm going to only involve something involving tan. So it's kind of going down a rabbit hole of case of making things a little bit more complicated. Now, your initial thoughts might be to do that, but if you do and it feels as if, right, hang on a second, this is looking a bit of a mess, I'm not really getting anywhere, just stop and try a different approach. Now, from this, what I've now got is that either sine x equals 0 or sine x plus cos x equals 0, because as you can see I've got two things being multiplied. I've got sine x and this bracket, and that all equals 0, so one of those two things must equal 0. So taking this as an example and knowing my sine graph, that if I just do a little sketch of my sine graph, now the values in which it's equal to 0 is at this point, and at that point there. So my x in this particular case is going to be 0, 180 and 360. And then looking at this particular case, well, the fact that I've got a single sine and a single cos, now if I take the cos x to the other side, I then take the cos x over to the other, so I end up with sine x equals cos x equals minus 1. I can then, using the first trig identity I've got here, I've got tan x equals minus 1. So whenever you've got a single sine x and cos x, like we've got here, you always kind of want to be thinking about changing it and combining it to make tan x. And then from this, I then inverse tan of minus 1, and I get an angle of 135 degrees. And if I use my graph, I get a second angle of 315 degrees. So giving me a combination of x between the range of 0 and 360 as being 0, 180 degrees, 360 degrees, and 135 degrees, and 315 degrees. And there is your final answer. So when you are dealing with solving trig equations and with a combination of different trig ratios, you always want to kind of think about those trig identities that are in that yellow bubble, as you can see. You also want to think about quadratics. You also want to think about factorising. So as we've done in this last example, it's not always a case of thinking quadratics. You can also think simple as well. And sometimes it's a bit of trial and error, and there's no harm in doing just that. As you're getting your head around this, there is always people think in different ways, and you might find that your initial thought might be the correct way. It also might be the wrong way as well, and there's no harm in you doing that. And again, the more questions you practice, the better you will become, and the more efficient you'll become as well, because you'll know exactly what to look out for. If you have any problems or would like any extra questions on these particular aspects of using trig identity to solve equations, just feel free to drop me an email at 162maths@gmail.com.